Good evening, everyone. My name is Aditya Sharma, and this is Aircraft Propulsion Course being conducted by Department of Mechanical Engineering IIT Guwahati under the NPTEL program. And we have already gone through week one and week two's content of this course. Now we are into week three of this course. And corresponding to that week's content, we are having this live tutorial session for this course. And the topics that we will be discussing for this week's tutorial is ideal and non-ideal Brayton cycle. Okay. Brayton cycle is the one that is related to your aircraft propulsion, right? Or turbojets, turbofans. So that is your Brayton cycle. And instructor for the course is Professor Vinayak Kulkarni from the Department of Mechanical Engineering, IIT Guwahati, and I am a research scholar here also. So we shall wait for a few minutes to see if somebody joins. After that, we shall start our session. Okay, so let's start with today's session. So ideal and non-ideal Brayton cycle. So first of all, let's see the contents. So we have majorly two main lectures and then questions related to those lectures. So we have lecture number 6, which is ideal Brayton cycle, where the compressor and turbine work ideally, isentropically, which is essentially isentropic. But in your non-ideal Brayton cycle, your compressor and your turbine will not work isentropically. Okay. And then there are this lecture 7 corresponding to the examples of ideal Brayton cycle, and then examples corresponding to your non-ideal Brayton cycle are in your lecture number 9. So in this session, we will have today's session. First, we will see this much, and then we will see this much. Okay. Then let's start with lecture number 6. Ideal Brayton cycle. So first topic is your air standard Brayton cycle. The processes involved in it. The schematic of your Brayton cycle when your cycle is open and when your cycle is closed. So we have discussed this, what is open and what is closed. Okay. Then heat and work interactions. This is important, and the estimation of state variables. So estimation of state variables and heat and work interactions. These two topics are very, very important. Then what is optimum work output? The work output that we get from our turbine. Okay. For a compressor, we gave work input, and from turbine, we get work output. Then efficiencies involved with the cycle. And then what is work ratio and what is back work ratio? Right? Specifications related to some engine if you want to give specifications for some engine. So these ratios can prove to be handy. And then what are the observations and analysis based on the topics we have discussed in ideal Brayton cycle. In lecture 7, there are examples. So one by one, let's see briefly the topics. Because this is a very interesting topic, so there is no haste. You can do it slowly. Also, we have a lot of time. Here, standard written cycle. Diagrams are very important, so I'll draw the diagrams. In terms of thermodynamics, if you draw various diagrams related to your ideal Brayton cycles, it will be like this. The pressure is constant here, entropy is constant, pressure is constant, and entropy is constant. Moves in this direction, moves in this fashion. This is U in, this is U out. From here you get work out. Here you get work in. Alright. I'm just drawing the thermodynamic cycles. So TS diagram, PV diagram, and your enthalpy entropy diagram. So 1 to 2, if you see, the entropy doesn't change. Okay. 3 to 4, if you see, entropy doesn't change. So 1 to 2 is your isentropic process, and 3 to 4 again is your isentropic process. Okay. Then at 2 to 3, your combustion takes place. Okay, so 2 to 3 is your combustion chamber, and then 4 to 1 is where the heat comes out, heat rejection. Okay. Processes. So 1 to 2 is your isentropic what? Compression. Okay. So this is your compressor, basically. 2 to 3 is what? Isobaric heat addition. And how do we do that? By means of a combustion chamber, right? Then you have 3 to 4 is very important what? Isentropic expansion. So how does this happen? This happens in a turbine, from where we get our useful work. Then 4 to 1 is your heat rejection, that too isobaric, which means In case it's a closed cycle, a pre-cooler is used. Right? Otherwise, the heat goes to your atmosphere if it's an open cycle. So this is it about the processes and thermodynamic cycle for your ideal Brayton cycle. I hope there is no doubt in it. Then if you see, second topic is your open cycle and closed cycle. So what are these? What is an open cycle and what is a closed cycle? So open cycle basically is one where the working fluid doesn't come back again and again in the same cycle. It doesn't close a loop. But in your closed cycle, the same working fluid will keep on moving, right? So this is fundamentally the difference between open cycle and closed cycle, and we have discussed this has been discussed previously also in either week one or week. Okay, so nothing more to add in it. After that, you have heat and work interactions. So from your heat and work interactions, so we can see now first process we will see compressor. 1 to 2 compressor we will see. Okay. So process 1 to 2. Okay. So about heat addition or about heat or work, if you have to comment about this process. So one thing you can comment is there is no heat transfer in this process, right? So Q12 is 0. You're talking about ideal case, right? And then work done to compress the air. So how can we find out that? So that can be done by change in the enthalpy. So if you see here enthalpy is H2, here enthalpy is H1. Okay, this is H2, this is H1. So difference in these two enthalpies. This basically is your compressor work, H2 minus H1. Now we can, for enthalpy, we can expand. So this can be specific heat at constant pressure and then multiplied by temperature, right? Static temperature. So this is your work input for your compressor. Then is your combustion chamber. Okay. This is your compressor. This is your combustion chamber. So what We can comment about it in terms of heat or work. So there is heat addition here, right? And how can we find out that? So again, your HS diagram you see based on enthalpies. Okay, so this is H3. So now this is your what? Combustion chamber. This is your compressor. So this is H3 minus H2. Again, expanding it. We will get this. Then we have process 3 to 4, which is 3 to 4. 3 to 4 is your basically turbine work. Okay. Isentropic expansion process 3 to 4, your turbine. So here work done by the turbine is this. Then similarly for your heat rejection case, Q out is H4 minus H1. Right? So this is it about your heat and work interactions in your ideal Brayton cycle. Then next topic is estimation of your state variables. Estimation of your state variables. So in it, some parameters are known to us and some parameters we need to find out. Okay, so what is known to us? Known to us is parameters like pressure ratio, inlet pressure at the compressor, temperature at the compressor inlet, the heat that we are adding, then the ratios of maximum pressure, maximum temperature to minimum temperature. Basically, T3 is where your working fluid exits the combustion chamber. So the working fluid will be at highest temperature at this. And T1 is where it enters the compressor at lowest. So this will be at lowest temperature. So T minimum. So T maximum by T minimum, T3 by T1. That is also so denoted by beta also. So these are known to us. So based on this information, we need to find out your network and efficiencies. So based on that, we can find out our other quantities like what is efficiency, W net, WT, WC. All this can be figured out, right? So this has been covered in detail in lecture number 6. So link I'll give in the description, right? Then next is your optimum work output. So optimum work output is there are two questions. So your in case of your optimum work output, your pressure ratio, optimum pressure ratio is equals to the under root of your maximum pressure ratio, right? For your optimum work output. And from there, what do you get is that your T2 is equals to T4 for your optimum work output. So these two temperatures, the entry of your combustion chamber and the exit of your turbine. So these temperatures are equal, right? Then efficiency, one formula for efficiency is efficiency of your ideal Brayton cycle is 1 minus 1 by, so this is your efficiency, right? Then is your work ratio and back work ratio. So your work ratio RW, the formula for this. So this basically is your W net by W turbine. So we have from turbine we have work, to compressor we give work, right? So the difference of these two is your net work that we get from the whole cycle. So WT minus WC is your net work. Then its ratio with respect to your turbine work is basically your work ratio, right? And this can be given like this. Your beta is your T3 by T1. So I have told now. Then back work ratio is your work input for your compressor to the work output from your turbine. All right. So this is your back work ratio. Then there are observations. So for observation, so this is in your last slide of your lecture 6. So observations like, so if you see your formula for efficiency, so this says that if your RP will increase, that is pressure ratio will increase, right? So your this second term will reduce. In that case, your efficiency will increase, right? So with increase in RP, your efficiency will increase. All right. Then for your work ratio, if you see in terms of your pressure ratio, so if you increase the pressure ratio here, what happens is your second term, the right hand side term, increases. In that case, RW will reduce. So for increase in RT, your RW will reduce. So this is with respect to your pressure ratio, the relations. Okay. For your efficiency and work ratio. So in observations and analysis, this much is fine. Other details can be seen from the lecture. Right. So lecture 7 was on examples of ideal Brayton cycle. Then we move on to our questions. Just give me a second. Yes. So this is your question. This is your first question. Which of the following statements is true for a Brayton cycle? Four options have been given, so you can try to answer. Prasanjit, you can try to answer. Okay, so first question, the Brayton cycle. So this, the options are related to your cycle efficiency. Right? Cycle efficiency is 1 minus 1 by this. I hope this is fine. Then based on your four options, so it depends on pressure ratio and maximum cycle temperature. Maximum cycle temperature is T3. Maximum cycle temperature T3 depends on RP independent of RP. So this is dependent on your pressure ratio. C option is correct. So about Brayton cycle, this question. The next question. Please read this question and try to answer this. So the question here says that question number two, for a Brayton cycle, which of the following statements for the slope of constant pressure line in TS diagram? Which of the following statements stands true for the slope of constant pressure line in TS diagram. So this talks about your slope of constant pressure line. So now what is constant pressure line? Let's see the TS diagram, the temperature and entropy diagram. So this is your temperature and entropy diagram. So here, what is a constant pressure line here? So if you see 2 to 3, if you see 2 to 3 is a constant pressure line. The line joining 2 to 3 is your constant pressure line. Then joining 1 to 4 again is your constant pressure line. So this means that P2 is equal to P3 and P1 is equal to P4. This basically this means that. Then with increase in temperature, what happens? So you can clearly see. If you see for point 3, the temperature is higher than 2, right? This, this. This is T3 and this is T2. Right? So if your temperature increases, the slope increases, right? The slope will, the temperature is increasing, your slope is also increasing. So that is one point we can say about your pressure line, constant pressure line. So options are it increases with increasing temperature, it decreases with increasing temperature, it remains constant with increasing temperature, it decreases with increasing pressure. Yes, so Prasanjit has answered A option. So A is the correct answer to this question. Okay. Because with as the temperature will increase, its slant, its slope will increase. Right, so A is the correct option in that case. Now let's move on to next question. Third question. After this question, we'll have numericals only. First for your lecture 6 and lecture 6 and 7, and then we have to discuss lecture 8, topics of lecture 8. After that, numericals related to lecture 8 and 9. Right. So, third question. Let's try to answer this question. So question says that for a given gas, for a given gas. So when the question says for a given gas, gamma specified, right? Work ratio of a Brayton cycle dash with the pressure ratio. It, what happens to your work ratio? So I have specified this. So if you see the options say that it will decrease, it will increase, it will first decrease and then increase, or it will remain constant. Now you see this. Sorry. So this is your work ratio. So what happens with your increase in pressure ratio, decrease in pressure ratio? With increase in pressure ratio, what happens? So if you increase the pressure ratio, this term will, what will happen? Because pressure ratio is in numerator, okay, what will happen? So this term will, if you increase the pressure ratio, this term will increase. this term will increase and the whole term will decrease because this is 1 minus, let's say this is term A. Okay, so 1 minus term A. The term A will increase with increase in pressure ratio. So from 1, you'll have to, more share will go out of this number 1. So work ratio will eventually decrease. So A should be the answer. Yes, A is the answer to this. Question. All right. So this is your question number 3. A is the correct option. I hope Prasanjit, this is clear. If there is some doubt, you can ask always. So no doubt. In that case, let's see question number 4 to 6. The paragraph has been given for question number 4 to 6. Please read this first and then we'll solve this. All this information has been given to us. The TS diagram, if you see, this compressor with turbine. This is combustion chamber, right? So P1 is given for this. P1 is given. Temperature is given at inlet of compressor. Then pressure ratio for the whole cycle is given, right? Then maximum temperature T3, that is at the exit of combustion chamber, is given. When two turbines are being used, not write it as this. The expansion takes place in two steps. First is 3 to 4, then 4 to 5. Okay. Let's say this is high pressure turbine and this is low pressure turbine. So this is taking place in two steps, expansion. High pressure turbine runs your compressor. So for that, this is the equation. And the work that we get as an output for our use is from your low pressure turbine, LPT, from 4 to 5. Okay. So this is basically the meaning of the paragraph that is given to us. So once we are clear with the paragraph, then we can move on to questions. I hope this is clear. If some doubt at some point, please let me know. I can explain that, or else we will move on to questions based on this paragraph. No doubt, Prasenjit? Okay. No doubt in that case. First question, exit pressure of high pressure turbine. So we need to find out the exit pressure of high pressure turbine. Okay. Question number 426. I'm solving question number. Let me go again. 1, 2, 3, 4. Sorry. 4, 5. And we need to find the exit pressure of high pressure turbine. P4 we need to find. So how we will do that? Because 3 to 4 is isentropic, right? So because 3 to 4 is isentropic. So isentropic condition we can apply here, okay, for pressure and temperature, which is this. The temperature and pressure can be related this way if the process is isentropic. But here, what do we know? Do we know P3? We don't know P3. We need to find out P4. And T3 is given to us. But is T4 given to us somewhere? T4 is not given to us, so we need to find out T4 also. So T4, P4 and P3 we need to find. T4, P4 and P3 we need to find out. But for P4, we need to find out P4 and P3 first, right? So we will find out these. How can we find out P3? You know, P2 by P1 is RP, implies P2 equals to RP P1, right? This we know. Other than that, because the line joining 2 and 3 is constant pressure line, in that case, P2 and P3 are also equal. Right? So from here, P3 you can find out. Then what is left is we need to find out T4. Now to find out T4, let's do something. Okay. So let's see that. So for your compressor, because compressor again is 1 to 2 is isentropic. So this implies this. Now putting the values, given values, T1 is 281 because 8 degrees Celsius, 273 plus 8, that is 281 kelvins. Right? And 6.5 is the pressure ratio. And gamma is 1.4, so this becomes 0.4 by 1.4. So if you solve this, this will come out to be. Please see if the calculation is correct, and if not, just let me know. So all this I'm doing to find out what T4. So all this I'm doing to find out T4. What is given to us? Compressor work is equal to high pressure turbine, right? So in terms of enthalpy, if you see, so H2 minus H1 is equal to H3 minus H4. I hope this is clear. So in terms of this specific heat, so this is this, and this is this. In that case, if you take T4 from here, this is T3 minus T2 plus T1. T3 is known to us. T1 is known to us. T2 is not known to us. So T2 we can find out from here. So that's why we found out T2 here. So now T3 is given to us. T1 is given to us. T2 we found out. So T4 becomes 1250 minus 479.69 plus 281. If you work this out, this will come out to be this. I hope this is clear. Now you'll find out pressure. Exit pressure for high pressure turbine. So exit pressure is P4. So from here we need to find out exit pressure. So P4 exit pressure is P3 divided by P3 divided by T4 gamma by gamma minus 1. All right. Now if you work this out, P3, how can we find out? Because P2 and P3 are constant pressure line or lie on the constant pressure line. So P3 can be equal to P2. P3 we have, T4 we have, there is nothing to worry about it. Then, so P2, from here you can find out P2 is RP P1. RP is given to us, P1 is given to us 6.5 into 115. In terms of kilopascal, Pascal, we will get the answer. This is this. So if you solve this, this will come out to be how much? Major part of this paragraph based questions is in this question. If you solve this, this will come out to be So this will come out to be 407.83 kilopascal. So this is your before, right? This. The next question is exit temperature of the high pressure turbine. So T4 we need to find out. How can we do that? Question number 5 solution. So W T4 we need to find out now. What this asks? Yes. This question asks at low low pressure turbine. Because high pressure turbines runs your compressor and then this is for your low pressure turbine. So we know the net work output is equals to your low pressure turbine, right? And this is given as 178 megapascal. That is 10 raised to power 6. And in terms of mass flow rate and enthalpy, this can be written as basically H4 minus H5. If you see this diagram, H4 minus H5. Right? Then now for the whole turbine, if you see, from 3 to 5, if you see, P5 by T3 is equal to P5 by P3, gamma minus 1 by gamma. Right? So from here, this can be found out. P3. Now P5 by P3 can be written as P3 by P5. This can be written as this. Right? Gamma minus 1 by gamma and multiplied by this. So this is your at exit temperature of your low pressure turbine. Correct. So T3 is given to us 1250 and the pressure ratio is given as 6.5. Gamma is 0.4, 1.4, gamma minus 1 is 0.4 and gamma is 1.4. Now if you do this, it should come out to be what? It should come out to be 732.23 Kelvin. So this is your basically exit temperature at low pressure turbine. Then sorry. Okay. So for low pressure, so this is for this answer is for high pressure turbine. This is for your T4 is this, but if you want to find out for T5, so we have found out for T5 this. All right. So now how do we find out the mass flow rate? So this is so this we have here W naught equals to W LPT, right? So 178 into 10 raised to 6 is equal to CP T4 minus T5. Here we need to find out this. This has been given to us. This we have, right? So Just putting the values 178 into 10 raised to power 6. So this will be in case this is low pressure turbine, you can write this. Otherwise, high pressure turbine for that is 1051.31. All right. So here we need to find out mass flow rate. Cp is 1.005 into 10 raised to power 3. P4 is 1051.31 minus P5 is 732.23. It implies mass flow rate is equal to 10 raised to power 6 divided by so if you work this out, this will come out to be this. Okay. So this is your question number 6. And moving on to next lecture. Before this, we'll have a short break of 5 minutes. After that, we'll continue. Thank you. So let's do this lecture number 8. So now because we are left with around 30 minutes only. So in lecture 8, I'll just briefly discuss the cycle, okay? And then not all the topics. All the topics you can check from the lecture itself. Link I'll give in the description. But one few questions to discuss, numerical questions. Okay. First, let me lecture 8. So Brayton cycle with non-ideal components. So this I can discuss so that we have the context. Lecture number 8. Okay. Let me draw this non-ideal Brayton cycle. Brayton cycle with non-ideal components. So it's TS diagram we'll understand and then we will do questions. So this is your TS diagram basically. Two, four, H2, H2 dash, H4, H4 dash. So what happens is ideally for your compressor, so compressor is 1 to 2 is compressor that we know. 1 to 2 dash. Ideally it moves from 1 to 2 dash. But in real scenarios, what happens is that work input is H2 minus H1. Right? For this work input is H2 dash minus H1. This should be this. But in real scenarios, what happens is work input that we need to give is this. Right? Let's say this is A and this is B. So B is greater than A. You can see this from the diagram also. H2 minus H1 is greater than H2 dash minus H1. So more work is required for the same transition, for the same transition from some pressure to this pressure, right? From this pressure line to this constant pressure, right? So the working fluid moving from to 2 dash or moving to 2, the pressure is same, right? But the work input in case of 2 is higher and in case of 2 dash is lower, which is the ideal case. Isentropic one is the ideal. Similarly, for your for your this one, sorry, 3, this should be 3, 3, 3 to 4 dash or 4. Is your turbine. So the work output that we get is ideally that we get is H3 minus H4 dash. And reality what we get is this is C, this is B. What happened is your B is less than C. Okay. Now you see H3 minus H4. That is real case. And you see ideal case H3 minus H4 dash, which is isentropic. So isentropically, if the gas expands, working fluid expands, in that case, we'll have more work output. But that is not the case. The real case is lower work output. Okay. And then there are efficiencies related to that. Right? So this around this the topics have been discussed. Be it your component efficiency, compressor efficiency, turbine efficiency, based on the enthalpy zone, right? Then estimation of state variables. So what are the knowns, and then from those knowns, what can we find out? Then is your heat and work interactions, right? After this is your optimum work output, right? Optimum work output. This is the beta. Beta is T3 by T. T max by T. Then maximum network from here can be found out. Then maximum efficiency also based on it can be found out. So expressions have been given in lecture number 8 for this. All right. You can refer to lecture number 8 for that. And then questions are there based on lecture number 8. So we'll jump to questions now. So let's see this. Question says that a simple gas turbine plant takes air at 1.2 bar, 320 Kelvin. Okay. P1, P1 compresses it to pressure of 5.7 bar. Right? So P2 is also given. The compressor has an isentropic efficiency. So NC is given. Then air passes to the combustion chamber. And after combustion, the gases enter the turbine at, so this is T3 is given. Gases enter the turbine at a temperature of 1275 Kelvin. So T3 is also given. Expansion of these gases take place to 1.2 bar pressure. Okay. This is P4, right? So P1 and P4 are on your constant pressure line. Then isentropic efficiency of turbine is NT is given as this, Cp is this, gamma is this. So all these things are given. So first question asks work input into the compressor. We need to find out H2 minus H1. Okay. T1 is given to us. T2 is not given to us. So first we need to find out T2. Okay. Question number 7. Okay. This series, question number 7. Given is T1 is 1.2 bar. T1 is 320 Kelvin. N compressor is 81%. T2 is 5.7 bar. T3 is 1275 Kelvin. And turbine is 57%. Then specific heat is this. Gamma is 1.4. Now, so isentropic relation will use for compressor, which is T2 dash by T1 gamma by gamma minus 1 is equal to P2 by P1. This is there. Okay. If you see 1 to 2 dash is isentropic and 1 to 2 is real. So 1 to 2 dash, for that we can isentropic relation use. Right? Now what we can take out from here, this is we have, this we have, and this also we have. So in that case, T2 dash by T1 0.4, sorry, 1.4 by 0.4 is equal to 5.7. Correct? After that, now we need to find out T1 is known to us, that is 320. So T2 dash is 5.7 into 0.4 divided by 1.4 into T1. T1 is 320. So if you solve this, this will come out to be 526.15 Kelvin. Okay. Now efficiency for compressor is given to us. Efficiency of compressor is this. So where it came from? It came from this. So this is coming from where? This is coming from comparing the enthalpies. What? H2 dash minus H1 by H2 minus H1. So we have compared this. From that, we have obtained this. Okay. So numerator will be low, denominator will be high. So this I have discussed. So 0.81, 81% is given. 526.15 we just calculated. T2 we need to find out. So now we can work this out. So T2 from here, what we will get is 574.50 Kelvin. Right? So work for compressor, work input for compressor is H2 minus H1. TP T2 minus T1, which is in kilojoules only. So CP we are keeping in kilojoules only. So answer will be in kilojoules or kilojoules. So this will be 255.77 kilojoule per kg. So this is it. This is compressor work, right? I hope no doubt. So 255.77. So this is work input into the compressor. Now next is actual exit temperature of the turbine. So we will now find out exit temperature of the turbine, that is T4. So T4 dash is ideal, but we will find out. Actual. So for that, we will use the efficiency of turbine that is given to us. So question number 8 solution. Now from 3 to 4, if you see process 3 to 4, 3 to 4 dash, this is isentropic. This is isentropic. For this, isentropic relation can be used. Right? Basically, N turbine is H3 minus H4, that is less than H3 minus H4 dash. Okay. So this essentially is this T4 dash. This is this. Correct? So here T3 is known to us, that is exit of combustion chamber. T4 NT is also known, 87% I believe, yes. And then this we don't have, this we don't have. Right, so if we can find out T4 dash, we can get the exit temperature at turbine. So how do we do that? We will use isentropic relation, that is P3 by P4 is equal to P3 by T4 dash gamma by gamma minus 1 implies this. From here, T4 dash can be figured out. T4 dash is equal to 1275 divided by 5.7 raised to power 0.4 by 1.4. So this will come out to be 775.43 Kelvin. Correct? Then now coming to, so T4 dash we have found out. So now end turbine is T3 minus T4 by T3 minus 4 dash. Implies 0.87 is equal to 1275 minus T4 divided by 1275 minus 775.43 implies T4 is, if you work this out, this will come out to be so I am straight away giving you the answer. So I have already worked this out. This is 840.37 Kelvin. Right? So the exit temperature of the turbine is this. Right? I hope this is clear how we found out exit temperature. Now we are left with found out T4. Before that, in the previous question, work input WC we found out. For that, we found out T2. Okay. T2, T4 we have, WC we have. Now back work ratio, that is WC by WT, which is H2 minus H1 divided by H3 minus H4. This is back work ratio. So question number 9. Yes. So this is basically T2 minus T1 by WC by WP equals to H2 minus H1 divided by H3 minus H4 is T2 minus T1 by T minus T4. This is 574.50 minus 320 divided by 1275 minus 840.37. If you work this out, this will be 0.58. So NB work ratio, back work ratio is this 0.58. I hope this is also clear. Then last question, cycle efficiency. 10. And cycle is W net by Q input. So this is WT minus WC by Q input. That is H3 minus H2. Now you work this out. This will be H3 minus H4 minus H2 minus H1 divided by H3 minus H2. I hope this is clear. These numberings are clear. Q input is for your combustion chamber. This real cases are these 1 to 2, 2 to 3, 3 to 4. We are discussing this one. And then this T3 minus T4 minus T2 plus T1 divided by T3 minus T. Now putting the values 1275 maximum temperature, 840.37 T4, 574.50 T20 divided by 1275 minus 574.50. This. So this will come out to be 0.25. So this is the cycle efficiency for your this question number 10 of paragraph second. So this is it about today's session. I'll conclude. In that case, any question you can ask. So two major lectures were there, lecture number 6 and lecture number 8. Lecture number 6 was on your ideal Brayton cycle, and lecture number 8 was on your non-ideal Brayton cycle. And then there were lecture number 7 and lecture number 9 on having examples of these two cases. So in Brayton cycle, the compressors and turbines work isentropically in ideal case. And in non-ideal case, these two components do not work isentropically. In that case, we take efficiencies of these two components in terms of percentage, how much they deviate from the real case. And then there is estimation of state variables. So based on the known components, how we can find out the unknown components when we have a turbine problem in our case, right? In real scenario. So this is it about week number three's tutorial. And the next tutorial again will be on next Tuesday. That I believe is on 19th, right? Timing will remain the same, 6 to 8 p.m. So till then, bye and thank you for joining this session.